So, for this particular case, we could assume that Cf into REL by 2 equal to G1 X star comma REL. Now, note that this is only when Prandtl number and Schmidt number almost equal to 1. Okay. So, we can rewrite this as Cf by 2 equal to Nu by REL equal to Sherwood number by REL. Okay. And because we assume this to be 1, we could also rewrite this as Nu by to Schmidt number. Okay. Simply because we assume Prandtl and Schmidt is almost equal to 1. Okay. So, this specific case of Prandtl and Schmidt equal to 1 just provides an idea as to what should be the relationship between the different characterizing numbers in these 3 boundary layers. Okay. So, this number, once again these 3 put together is called as the Stanton number for heat transport. Okay. And these 3 put together is what is called Stanton number for mass transport. Okay. This is Stanton, STAN. So, you will start seeing all kinds of dimensionless numbers that will start propping up hereafter. You are not expected to remember all the expressions for these dimensionless numbers, but what would be useful is if you attempt to understand what does each of these numbers signify. For example, Nusselt number is the resistance to conduction in the fluid divided by convection, resistance to convection across the interface. Similarly, Prandtl number is the ratio of momentum diffusivity to thermal diffusivity. So, if you understand what these different numbers characterize, that is good enough. You should actually be able to systematically find out what is the expression for each of these dimensionless quantities. Okay. So, this relationship that Cf by 2 friction coefficient equal to the heat transport Stanton number equal to the mass transport Stanton number is what is called as the Reynolds analogy. Called the Reynolds boundary layer analogy or simply Reynolds analogy. So, this is very commonly used in different types of heat, mass and momentum transport calculations, because it is very handy. If you know you are able to measure the momentum boundary layer properties and are able to find the friction coefficient, you are done. You know the Stanton number, you know the mass transport Stanton number, and all you need to know is Reynolds and Prandtl, you are done. Your heat transport coefficient and mass transport coefficient comes for free. Because Reynolds number depends upon the properties of the fluid and the properties or the length of the plate that you are looking at, and Prandtl number and Schmidt number are essentially properties of the fluid. If you know the properties and if you are able to measure either of these 3, any one of these 3, the other 2 comes for free. So, this provides a powerful method for calculating the heat transport coefficient and mass transport coefficient. Moment you know what is Nusselt number and what is Sherwood number. So, remember that these 2 are characterizing numbers for heat transport coefficient and mass transport coefficient. So, if you know Nusselt number, if you know Sherwood number, you are done. You have found the heat transport coefficient, you have found the mass transport coefficient. Remember, we haven't solved the equations yet. We have not even solved the equations. Without solving all of these 3 equations, if you know one of them, if you are able to even experimentally measure them, let us say we do not even solve the equations, you are able to experimentally measure either of these 3 quantities, you are done. The others come for free. So, that is a very powerful method. In fact, that is the power of these analogies. Now, remember that this Reynolds analogy is valid only when Prandtl and Schmidt are equal to, approximately equal to 1, right. So, the question is, real systems are obviously not the case. Prandtl and Schmidt are obviously not 1, because we are not always looking at dilute gases, we are looking at other systems too. So, that requires the next, that takes us directly to the next topic, which is the modified Reynolds analogy, or it's also called as the Chilton-Colburn analogy. Also called as the Chilton-Colburn analogy, where the analogy assumes that Prandtl number is not equal to Schmidt number, and obviously it's not equal to 1. Okay. So there is no analytical way of finding out what is the equivalence between the 3 transport mechanisms in the boundary layer, if this is the case where the Prandtl number is not equal to Schmidt number. But then observing the functional form, okay, you look at the functional form, and then one can define what is called the Colburn factors. So the functional form helps in deciding and this is valid for okay. So this is what is called the Chilton-Colburn analogy or modified Reynolds analogy. So what Chilton and Colburn independently did is they took the Reynolds analogy, the functional dependence of this friction coefficient and the Stanton numbers, and observing that Nusselt number goes as G1 something into Prandtl to the power of n. So now the question is, what is n? So they found, and these were done by all kinds of experimental studies and correlations, where they found out that this n actually goes as 2 by 3. Okay. Now, not just that, we are also going to find, so this is the analogy, Prandtl number to the power of 2 by 3 multiplied by Stanton number gives you what is called the Colburn factor. So this J is called the these are called the Colburn factors. Okay, these two are called the Colburn factors. So if you know the friction coefficient, then you should be able to estimate what the Colburn factors are. And once again, if you know the Colburn factors, you're done. So this is for a real system with certain range of validity for Prandtl and Schmidt number, which sort of encompasses most of the systems that you would probably experience in the real system. Okay. Okay. 1 second. Yeah, what's your question? Right, right. We're going to see that. We're going to see what's the functional form of Nusselt number very soon. There you will see that it actually scales as 1 by 3 and sometimes it actually scales as 0.4, 0.33 and 0.4. We're going to see that in a short while, mostly in the next lecture. Alright, so we said that Lewis number, okay. So Lewis number is the ratio of Schmidt number to Prandtl number, okay, nu by DAB, thank you, into nu by alpha, oops, alpha by nu. So that's alpha by DAB, right? Okay. So now we said that Nusselt number divided by Prandtl to the power of n, okay, that should be equal to Sherwood by Schmidt number to the power of n, and that has the same functional form. That has the same functional form. So now if I open up the expressions here, Nusselt number is h into L by Kf, that's the heat transport coefficient multiplied by length of the plate divided by the corresponding conductivity, that's equal to Hm into L by DAB into PR by SC to the power of n, right. So now from here Hm, which is the mass transport coefficient, divided by heat transport coefficient. Okay. So that ratio is now given by dAB by Kf into Lewis number to the power of n. Okay. So we know that Lewis number is Schmidt by Prandtl, and so that simply gives you that dAB by Kf into Lewis number to the power of n. So Hm by H. Now Lewis number is defined as alpha by dAB, right. So now we can multiply and divide by rho Cp dAB by alpha, right. So all I have done is I have found Kf by rho Cp. So alpha is conductivity divided by rho Cp, that gives you thermal diffusivity. So I have introduced a definition into Lewis number to the power of n. But we also know that Lewis number is alpha by dAB, right. So from the expression that we have written there. So that will be rho Cp Lewis number to the power of n minus 1, 1 minus n, n minus 1. Okay. So did I get it right? Something is wrong. Should be 1 by rho Cp. Rho Cp, sorry. Okay. So now, so ratio of heat transport coefficient and mass transport coefficient is Lewis number to the power of n minus 1 by rho Cp. So that is an important observation. So Lewis number is alpha by dAB, okay, and rho Cp, these are the properties of the fluid. Because of the analogy, you see that the ratio is now going to remain constant. It is going to be only a function of the properties of the fluid. Not more, not just that. Supposing if I look at the average mass transport coefficient and average heat transport coefficient, okay. What's the definition of average mass transport coefficient for a flat plate? One by L integral 0 to L Hm dx divided by 1 by L H into dx. Okay. So now we can use this expression for local heat and mass transport coefficient, and so we can rewrite this as Lewis number to the power of n minus 1 by rho Cp into integral 0 to L H dx and so that will be by rho Cp, right. So that is an important observation. Not just that the ratio of local mass and heat transport coefficient depends only on the properties and constant, and that is also equal to the ratio of average heat transport coefficient and mass transport coefficient. So that is an important observation. So if you know the local quantities, then you should be able to relate the ratios of the average quantities. Now this we have shown for a flat plate case. You could actually show similar expressions for other geometries too. So if you know the local ratio of the local heat mass and heat transport coefficient, you should be able to find out what is the ratio of average heat transport coefficient and average mass transport coefficient. So when we define these average mass transport and heat transport coefficient, I briefly alluded to the fact that what is really important from practical point of view is these average quantities. Although we are trying to estimate all the local heat transport and mass transport coefficients, but ultimately what you would be using in your experiments, which is some of you have already done in your laminar flow and turbulent flow experiments, and others would do that through the rest of the semester in your lab course, is that what you would actually be using is actually the average heat transport and mass transport coefficient. The reason why you would use the average is what you can measure. Supposing if you have a double pipe heat exchanger, okay, You have concentric pipes, there is fluid flowing through the inside pipe and there is fluid flowing between the two pipes and there is heat exchange between them. So what you would actually measure is the temperature of the fluid that is inlet to both these streams and outlet to both these streams. You really cannot measure the temperature at every local point inside. So what is of real practical importance are these average quantities. So ultimately what we will see over and over again many number of times is how to find average mass transport coefficient and average heat transport coefficient. Okay. But we said that the local heat transport coefficient, you need to find Nusselt number, and if you want to find the local mass transport coefficient, you will have to find the Sherwood number. So therefore we will have to define Nusselt number and Sherwood number based on these average quantities. So if you want to find average heat transport coefficient, then you need to know what is the average Nusselt number, and that's given by H bar L by Kf, and similarly you will require the average Sherwood number, which is average mass transport coefficient divided by multiplied by L divided by the corresponding diffusivity. So that's what you will have to find. So for all the different geometries that you will discuss in the next several lectures, the ultimate goal is to find out this average Nusselt number and average Sherwood number. Okay. So with this we sort of finished the basic boundary layer approximations and analogies, and we are going to move into the specific different geometries, and this is where we are going to attempt to solve some of these model equations. Remember that so far we have not solved any of them. We have only looked at the functional form, structure of the equations and some intuition that we used for boundary layer approximation. Based on that we were able to guess, we were able to get all kinds of insights and information about the processes that are occurring in boundary layer.